Today I'm here. I'm very happy to be here. I don't know why I'm here, so maybe we'll discover together. I'm coming from this world. You see, what you see is a Photoshop work, but on the background, this kind of eye is our detector. We call it detector. Is like a building, is a 4 or 5 story building weighing 15,000 tons. So as particle physics are really coming from material world, we use detectors, material, to investigate matter, to investigate material. What is the origin of the universe? What is the deepest, most intimate structure of matter? But you will see soon, I'm pretty sure, that we are not interested in matter. Basically, at the end, once you explore the origin of matter or the deepest structure of matter, you are in the world of concepts, ideas that are very close to immaterial world that you are trying to describe. So I found the title of this meeting quite interesting. I start with something that I like very much. Amenhotep III, the Magnificent, and I like the fact that there are these two beautiful representations. One is realistic, actually beautifully realized in terms of art, and this material is wood. And the other one is idealized, is Amenhotep III in form of God, and material is granite. Granite is a persistent material that will last for millennia, as we know very well. So there is a clear perception of the, let's say, fragility of the man and the persistence of the god that are mixed together in the figure of the pharaoh. So we are talking of matter which is basically, if I would use a phrase, I would say is a source of information for you, but also for us. So basically, investigation of matter, meaning trying to collect information. That's it. Give me a piece of matter. As a scientist, I'll give you basically a huge amount of information, much more than what you think today would be possible. You use many tools that we have developed for other activities, like tomography or like spectroscopy or luminescence or diffractometry. I can list a huge amount of modern tools, but there will be others that will be available very soon based on what we are doing in trying to understanding the deepest structure of matter. And we extract information from matter and we try to understand our own civilization. We try to understand the roots that we have. So what you are doing is extremely important to understand why we are here. What are the scope of our existence in this beautiful planet? But at the end of the day, what is matter exactly? This is the question in which maybe I can be helpful, or maybe I can destroy the idea that you have on this material that you use daily to develop your studies. What do we know today of its most intimate nature? How resilient is ordinary matter? There is somehow an intrinsic fragility within any material form. Those are the questions that I'll try to answer, again, from my perspective. The first thing, in my view, you are contemporary historians. As Egyptologists, I mean, we're talking of 3,000, 4,000, 5,000 years ago, so modern history. Our universe is very old, extremely old. If we take a rock of the Dolomites, we are talking of 250 million years. And again, yesterday. The solar system is, again, 4-5 billion years. Then this is really seriously something in our past. And the Big Bang, basically our universe is born 13.8 billion years. So let's say our calendar is made of billion years. This is why million years is an instant. And the universe that we study is old and very cold. This is not we always complain when there are temperature around 30 degrees on planet Earth or 40. The global heating is a worry, a serious worry we have. But we should never forget the average temperature of the universe as a whole, as an object, is extremely low. Is 2-3 degrees above absolute zero, so minus 270 centigrade, okay? So we are talking of an object in which in its average temperature is jelly, frigid, extremely cold. Clearly we have a prejudice because we live in a warm planet, and so we think that everything is basically around this temperature, but this is not true. We are the exception. We live in a point, in a corner, which is completely different from all the rest. And if you want to be sure, you just fly, and when you see the pilot say we have reached the cruising altitude, temperature outside is minus 50. So you are at 8,000, 9,000, 10,000 meters from the surface of the Earth, and the temperature drops already to minus 50. Imagine if you reach the outer space, you go down to minus 270, okay? So the issue for us is that we cannot study the composition of this very old and very cold object. I use these two pictures of a newborn and a man exceeding 100 years age. That clearly is difficult to understand the baby universe studying the old universe. No? So you have to invent something. We have to be creative, no? Because otherwise the situation will be completely different. We have behavior which are completely, it's difficult to relate the behavior of matter very cold and very old with the behavior of matter very young and very hot. No, this was the baby universe. So we have to invent something. And this is what we have invented. We have invented two different roads. The one on the left is the road that I follow. I'm particle physics. We use a super microscope. Basically, we study the tiniest possible object. So we try to investigate the structure of matter. That means that we investigate the smallest possible dimensions. An atom for us is a huge object. We investigate objects which have the dimension which are, let's say, 100 millions smaller than an atom, 100 million times smaller than an atom. So clearly is a completely different world. To do it, what we use a particle accelerator. We accelerate particles, very small particles, proton in our case, and we make them to collide. And during the collision, we create matter particles that are not existing today. I cannot go in the market and say, give me half a kilogram of Higgs boson, because they are not available here, because the universe today is too cold for the Higgs boson to live happily. No, he was living happily in the very first instant of the universe when the average temperature was billions and billions of degrees. So we try to reproduce this environment in a very tiny amount of space. This is the space that is created during the collision. This is why during this collision we can recreate the environment to have the early particle of the universe to flourish, and then we can study them. They live for an instant, for a fraction of a second, but it's enough for us to study their properties. On the other extreme, there are the astrophysicists, the astronomers. They study the largest possible object. They study stars, galaxies, clusters of galaxies, the entire universe. So their dimension is the dimension of the universe, 10 to the 28 meters. So you see the two extremes. No? And what they use is a very simple trick. No? The speed of light is limited. If you are able to see something very far away, you see something in the past. Very simple, because light travels at 300,000 kilometers per second. So if you have an object, a galaxy, which is 1 billion light years distant, 1 billion light years distance, you see the galaxy as it was 1 billion years ago. So you look directly in the past, looking at very far object. No? If you are able to see a galaxy or a cluster of galaxy which is far away, 10 billion light years, light employs 10 billion years to reach our telescopes, you see the galaxy or the cluster of galaxies as it was 10 billion years ago, at the beginning, at the birth. So this is why they are able to investigate and study the origin of the universe. You see two different paths, and what I call the miracle is that the two stories, the two details that are produced by the two groups of scientists coincide. So they are consistent. So we study the particle, the elementary particles. We tell a story of the origin of the universe, which is identical to the story that is told by our friends, astroparticle physicists, and astronomers. That give us some confidence that the story is solid, no? Because there are huge amount of confirmation, experimental observation that confirm this story. This is our playground. So we're talking really of large infrastructure. It's the LHC, 27 kilometers in the region of Geneva, 100 meters downstairs, and this huge infrastructure that we have built to produce and study the collisions of high energy particles. What we have understood of matter is quite simple. Basically, ordinary matter, I call it ordinary matter because this is outside the discussion of today, but there are other forms of matter that are completely exotic, different from what we consider normal matter. It's basically made out of particles. No, we call them modern atoms, although they're completely different from the Democritus approach. So an atom, as it is today, is an object which is 10 to the minus 10 meters. This is the typical dimension of an atom. An atom is made out of electrons and a nucleus in which there are particles that we call protons and neutrons that are charged or neutral. Is a very, very tiny component of the atom. The largest part of the mass of the atom is concentrated in this nucleus, but the nucleus is not elementary. No? Again, it's made out of other particles which are made out of other particles. It's like a Russian doll. No? You open the doll and you see another doll. And today, so far, we have reached the doll that has a dimension of 10 to the minus 18 meters. And these are quarks. The dimension, typical dimension of a quark maybe is less than 10 because we have not yet able to really measure the dimension, but we are sure that those objects are smaller than 10 to the minus 18 meters, and the electrons has similar dimension. We call these particles point-like because we are not able to see if they have a dimension and which is exactly the dimension. Basically, this is the knowledge we have today of ordinary matter is the standard model of particles, and it tells us that matter is made out of quarks and leptons, you see on the left side, red and green families. Quarks, you know, are for the Italian Piero Angela program, are the leptons is the electrons that is used for the washing machine. And then this particle exchange the forces through other particles. So this is a completely different approach with respect to the old atomistic approach. No? So there are particles producing matter and other particles keeping together matter. No? So it's important to note that not only because this creates a difference with respect to the trivial idea of considering the particles small balls. No, they are not small balls. They have something completely different from what we usually consider as a piece of matter. And the most important thing is that there are particles that bring interaction, bring forces. The simplest example is the photon. The photon which is now coming from this light on my face and you can see it. These photons carry an interaction, carrying the electromagnetic interaction. So are particles that are everywhere, are particles and fields. Are elementary particles or over field that can reach the entire universe. There are fields or forces that are less known because they are concentrated in the subnuclear world, like, for example, the W and Z, these two letters, those are the particles carrying the weak interaction. Forget it, is an interaction which produces some decay. Is an interaction that does not keep together matter, but produces the decay of matter. is important, very important. Without it, the sun will not be able to work. So it plays a key role, but is not relevant for the discussion of today. While the G is the gluon, is the strong force. This is very important to keep matter together. In addition to this, there is gravity, which is not in the standard model. Gravity is a force that you know very well, is the one that on which you fight to stay, to stand, to stay, to walk or to climb a mountain. Gravity keeps together planets, star, galaxy, and so on. And everything boils down to a very simple hierarchical organization that I summarize here, basically. At the basic level, there are protons and nuclei, which are produced through quarks, and gluon, basically, are kept together by the strong force. So the strong force keep together the proton and keep together the proton among them in the nuclei and protons and neutrons. So this is at very low distance is the kingdom of the strong force. The gravitational force doesn't matter. Electromagnetic force is not important. So protons are positive, but the strong force is so strong that the fact that two protons repels each other doesn't matter. Protons are massive, they have some mass, so there is gravitational attraction between them, but doesn't matter. It's so weak, it is overwhelmed by the strong force. So if you study a nucleus or a proton or a neutron, you can forget electromagnetic or gravitation interaction. They are irrelevant. Once you go up to atoms and molecules, you see now the structure that are quite familiar to you. You forget the strong force. Strong force is confined in a world which is much smaller. Now the dimension of this object is so large that the strong force does not act anymore. It is confined in a very small amount, in a very small dimension. So this is the kingdom of electromagnetism. No? Only electromagnetism works. So atoms are kept together by the electromagnetic force, molecules are kept together by crystals. All these structures are produced through electromagnetic force. You can ignore gravity, you can ignore strong force. Then you move up in the organization and you reach bodies, macroscopic bodies like me or like the planet or like a pyramid or like a galaxy. And in these macroscopic elements, basically planets, stars, galaxy, only gravitational force is important. You see, this hierarchy helps in dividing the three kingdoms. If we go now to the components of matter at the deepest level, I call protons the immortals. The talk is resilience and fragility. So we are lucky because matter has found a way in which it can organize itself in a way that could last for billions of years. This is why we are here. And the trick is to have these three quarks, actually three quarks, but two different families, up and down, one family, two different kinds. Those are the lightest quark. A proton is made out of three quarks of the lightest type, kept together through gluons, through the strong force. And the trick is very simple. Clearly, we are talking of a very small object, 10 to the minus 15, remember. No? But it's an object which is 1,000 times larger than a quark. So if you have now a proton in your imagination, you don't see the quark. They are very tiny objects, not a very small object. And the trick is that the mass of this object is very light, 10 GeV, 10 MeV, sorry. While the energy which is spent to keep them together, the glue is 1 GeV, is 100 times larger. So to keep together a very light object, you use a huge amount of glue. And clearly, this object is very solid, is very stable, no? Because it is using a huge amount of force to keep together very light elements. So there is no hope that they escape away, they go away. There are studies trying to understand the lifetime of the proton, and we have been able only to put limits on the lifetime. So, and the current limit is 10 to the 33 years. Imagine the age of the universe is 10 to the 10 years. So the protons of our body, or the granite of Amenhotep, or this table, were produced 13.8 billion years ago. And they will last for many, many billions of years, even when our solar system will be destroyed. The protons that belongs to our body or belongs to the artifact that you are using are sort of immortals. No, it's very difficult to imagine a way in which you can destroy them. You can do it, but it's very, very unusual. The same is for the electron. You see, now you understand why we are so lucky. No, atoms are made of protons, neutrons, and electrons, and those are very stable parts. All the other particles produced through the mixture of those quarks and leptons are not as stable as those ones. Those are, they decay immediately. No? So we produce them. We produce a huge amount of zoology of particles. We combine them in all possible combinations, but they don't have this gift of living for billions of years. There is none of them living for this amount of time. No? Those are very ephemeral lives, really decaying or disappearing within a fraction of a second, 10 to the minus 10 seconds, so an incredibly short amount of time. It appears that basically our universe has been able to develop this story, which is very long, thanks to this. Thanks to the fact that in the very early beginning, this kind of sort of organizational structure was produced. There will be even the possibility to survive what I call the mother of all catastrophes. If we are not able to destroy our planet before, we have definitely a clear end, which is written in the mechanism, the behavior of our sun. So our solar system depends on our sun. And our sun is a star which is in the middle of the life. Basically, evaluation is that there are other 4 or 5 billion years for the sun to survive, because at the end it will exhaust the hydrogen. The hydrogen is needed to produce the nuclear fusion. Without the nuclear fusion, there is no heat, no light, and the sun will sort of explode, expand. Basically, there will be a moment in which the sun will expand and will reach the earth. So everything will be, so even the museum, I'm sorry, despite all your cares to preserve, there will be no escape. Everything will vaporize, basically, very rapidly, very quickly, but not the protons. The protons will stay. So there is some, so take the positive aspects. We have something that will stay, and also, let's put this way, I'm always optimistic. We have 4 or 5 billion years to find another planet in another, maybe, so maybe, why not? Basically, this is what will happen. There will be a sort of nebula, a huge, we see something like this, which will be our destiny already happening in our part of our galaxy. We see, for example, these huge clouds that are generation of stars that have exploded and produced this nebula of material, mostly is hydrogen and helium, plus an amount of heavy material. And these are the nebula that originated our solar system. So basically, don't be sad too much. We will probably be origin to another solar system, maybe in another few billion years. So. But the fragility of our material world is not an issue only connected to the catastrophic end of our sun. There is something more subtle, and this is probably what is, for me, is important, particularly because we have discovered it very recently. So it's not something that we knew since ever. Now we come back to the origin of the universe, and I want you to concentrate the attention to this moment. The Big Bang has happened already since 10 to the minus 35 seconds. So it's a peanuts, no, in terms of seconds. But now you see this, this universe is like a soccer ball. Imagine this. No? Imagine 20, 30 centimeters. It's a microscopic object already. It is expanding very quickly, but now we have frozen the movie and we see the universe as it appears. And you see, it's a perfect universe, no? Because uniform everywhere, no? Isotropic everywhere, but it's completely useless. No? So if we would have continued this way, we will not be here. It will be maybe still perfect, but without any structure, any form, a persistent form of matter. Luckily for us, something happened in an instant later, 10 to the minus 11 seconds. So again, very small amount of time. The universe continued the expansion, the temperature was dropping, and it drops below a certain melting point that we now know very well. At this melting point, what we call the Higgs boson froze, basically. No? So up to that point, the Higgs boson were flying everywhere. So imagine the universe, the perfect universe, were made of the same particles, but everything was, all particles were massless, and they were all flying at the speed of light. No mass, speed of light, like a photon. No? And if the particle fly at the speed of light and they have no mass, they cannot aggregate. They cannot form any persistent form of matter. But luckily for us, at this moment, there is this change of phase, a catastrophe, a real catastrophe. No? There is one of these particles, which is the Higgs boson, that freezes and produces a sort of web, a very subtle web that interacts with all the other particles. So the other particles now found something in this universe, which is this newcomer. And this newcomer is active. So they interact. Some of them interact very strongly. Some of them don't feel at all the presence of the Higgs boson in the universe. And so the one that don't feel at all the presence of the Higgs boson stay massless. Like the photon. The photon is neutral for the Higgs boson, does not interact with the Higgs boson. But other particles like the quarks or the leptons, they started interacting. And some of them became very heavy. So they were slowed down by this field. Interacting with this field, their speed was reduced substantially. Others were slowly reduced, just a little bit. So some of them became very heavy, some of them became heavy, some of them light. And this was the trick, no? Because having this difference, universe which is not anymore perfect, allows the possibility of matter to organize. So we are here because there has been this magic moment in our history. And this is what we call spontaneous breaking of the symmetry. So we have lost the beauty of the symmetry, but we have gained stability. Stability at the level of billions of years. So now matter is not anymore identical. There are heavy quarks, light quarks, some of them can organize. And so at this point, some of the elementary particles that are not massless, that gets some mass, can organize themselves in form of protons and neutrons, and then atoms, and then gas, galaxies, planets, everything, including us. So in some sense, we have discovered this thin fabric shaping our universe, but this thin fabric is intrinsically fragile because it's due to a mechanism. It's not something intrinsically given to the matter in itself. It's coming from, if the mechanism breaks, the entire universe will disappear in a form that will be similar to the perfect universe of the very beginning. So again, in each form of matter, there is an intrinsic fragility that comes from the intimate structure of all material form, including the ones that appear eternal and say, living forever. So thanks to this mechanism, the story can continue over billions of years, and we are here. Thank you very much.